So like Zach said, I'm Sam, and I'm going to be talking about doing extreme mass ratio inspirals with the Einstein Toolkit. So first things first, of course, what is an extreme mass ratio inspiral? So Emory's are a special case of binary mergers where the mass ratio epsilon is much less than 1. So generally, this will make sense later, we refer to it as having a very small mass ratio. Some people tend to refer to extreme mass ratio inspirals as having a very high mass ratio. It just depends on which way you're putting that fraction, right? But it's the same thing. So Emory type systems are one of the main things that you would expect to see them in is galactic centers, where you have black holes or neutron stars inspiraling into the supermassive black hole. So the main point here is that one of the objects is so much larger that it is almost unaffected by the other body. Generally, the mass ratio is going to be something of 1,000, 10,000. The bigger object is just way more massive than the smaller one. And so this sort of orbit of the smaller body slowly shrinks until there's a sudden plunge into the supermassive black hole. Now, one of the things that's a little different here is that these orbits can be highly eccentric. And while the eccentricity does decrease over time, it's likely still significant even just before the plunge. While a lot of other more similar mass tend to sort of circularize, these keep their eccentricity for most of the inspiral. Now, Emory's are expected to be very important events for LISA, which is the planned space-based gravitational wave detector. So they're not in LIGO's detection band, but for LISA, they're going to be right in its expected band. So it's very important that we have simulation tools for Emory's so that we have waveforms so that LISA can look at them, right? I mean, if we don't have the waveforms, there's going to be a problem. And so that's sort of what the self-force community has been working towards, is some sort of developing the codes necessary for these systems. And here's just something from NASA has this artist picture of just how much bigger the other, right? There's the small one that's sort of just orbiting around and slowly inspiraling into the central body. So what is the motivation for the self-force approach? So in a binary system, the evolution is greatly affected by mass ratio. And so decreasing the mass ratio increases the total time it takes for the system to merge and become a single body. But it also decreases the maximum step size that you need, which greatly increases the computational cost, because we're saying we need to simulate it for longer, and we need each time step to be smaller and smaller. So this is bad on both sides. So traditional numerical relativity techniques simply aren't viable at these lower mass ratios because of the scaling issue. But in the extreme limit of the mass ratio, we can instead take a perturbative approach where we expand in order of this mass ratio epsilon. So in this framework, the orbiting body, which we're going to refer to as a particle and pretend it's a point mass, regardless of what sort of compact body it is, perturbs the background space-time of the central body. So these perturbations interact with the particle and accelerate the orbit, causing the inspiral. So in this case, instead of considering the sort of actual space-time that's perturbed, what we do instead is consider a background space-time from the central body, and then we have an accelerated orbit of the particle. So also there's a simpler case. You can look at the metric perturbation, but there's a simpler case of a particle with some scalar charge Q. And this is often used as a sandbox for developing new numerical techniques, because in that case, we're only evolving the scalar wave equation instead of the whatever evolution equations fall out of Einstein's equations for the metric perturbation. So the general self-force approach is to perturbatively expand the space-time metric in the mass ratio. And with this, we have some full metric G tilde, and this expands into some background metric G, and then each of the various perturbation orders with epsilon H1, epsilon squared H2, etc. So G is some background metric, usually Schwarzschild or Kerr, something like that. And then Hn is the nth order metric perturbation. So at 0th order, this is going to be a particle that's following a geodesic in the background spacetime. To first order, the particle instead is following a geodesic in the perturbed spacetime, this g plus epsilon h, but this is equivalent to the particle accelerating in the background spacetime. And so the self-force approach takes this alternative perspective of it being accelerated in the background. So there's several ways one can compute these. So there's sort of frequency domain codes, and then I'm going to talk about two different sort of broad categories of time domain codes. So the frequency domain codes are the most accurate codes within their region of validity, and they're very well developed at this stage. However, they're only valid for periodic geodesic orbits, which inspirals aren't. So that's a problem. They can't capture the physics during the plunge. So also increasing eccentricity, of course, does require more frequency modes, which is going to increase the computational cost. And many Emorys are expected to have high eccentricity. So even if one wanted to somehow piece together multiple frequency domain simulations or do something like that, the problem is you're going to have to run a lot of different ones with high eccentricity, and that still won't get you the plunge, right? So there's sort of, you can't really build the whole waveform with frequency domain codes, but they're great for comparison purposes because they're so high accuracy. On the other hand, there's adiabatic approximation codes. These assume that the self-force can be described by some orbit average quantities. How exactly they average them and what exactly it neglects to capture about the physics sort of depends. But generally, they usually include the dissipative part of the self-force, but ignores the conservative part. So what this means is that it introduces errors into the orbital phase and gravitational waves. And has insufficient accuracy for parameter estimation for LISA. These might be capable of detecting that there's an Emory in the data. That remains to be really verified until LISA exists and we have real data, but it would definitely not be enough to do any sort of parameter estimation. The self-consistent method, which is what we're using, uses the full self-force calculated at each time step to drive the evolution. So to explain sort of how this is calculated, first let's look at sort of how we decompose this field. So we've got, so the problem here is that we want to calculate this force acting on the particle, but the field generating that force is its own metric perturbation. And of course, a part of this being treated as a point mass, its own field is singular at its location. So we have to somehow resolve that singularity in the field. Now we can look at radiation reaction in electricity and magnetism to sort of have a comparison case to see sort of how this works. So if we consider a charged particle moving in a circular path, producing some electromagnetic vector potential, where we have some current J, then the particle is going to emit outgoing radiation, and that causes it to spiral inward. And this is generally referred to as the retarded solution. Now we can, of course, time reverse this and get ingoing radiation with an outward spiraling particle called the advanced solution. Now, if we want a version of this system where it's just orbiting and not in spiraling or outward spiraling, just sitting on a circle, then we can simply construct that by adding the two together, dividing by 2, and we have this symmetric, or in this case, also can be referred to as the singular solution. Now, all three of these solutions have the same singular nature at the particle. So the regular field that actually generates the force on the particle, in the case of, say, the retarded solution, should just be the retarded field minus the singular field, because we're subtracting off the singular piece, but leaving some regular field that generates the force. Now, this does get a bit more complicated in curved space-time and how exactly one constructs this. I'm not going to go into that. There's something called the Detweiler-Whiting decomposition if you really want to go look at it. But suffice to say, this is sort of how we get a field that we can actually use for the force. Now, how exactly do we actually calculate this? Because while that's all well and good on paper, numerically, we still need to subtract two singular terms to get the regular term. So there's two general approaches. One is mode sum decomposition, which decomposes the fields into spherical harmonic element modes. Then the retarded and singular fields are expressed as an infinite sum of finite fields, and the singular field, not the regular field, can be calculated with multiple decomposition, which is a little bit faster, but still it's very computationally expensive. We're having to decompose the retarded field into LM modes, subtract off the singular field, recombine, and this is just very expensive. The alternative that has been come up with is the effective source approach, which is also sometimes referred to as the puncture approach, merely as a sort of reference to the NR puncture methods. So what it does is it directly regularizes the source with an approximate source function. So it uses a window function, so the source is just sort of right around the particle, because we don't want to smear the source all across space-time, right? We want it to be very local. So there's this little window function. So around the world line of the particle, there's this sort of world tube where the effective source exists. And outside of that, the effective source is zero. And this is carefully constructed to ensure sufficient differentiability. And this is very well described in how one gets the differentiability they want. So on and so forth, right? And the benefit of this is it's much computationally cheaper than the mode sum decomposition. So the effective source, we just have this, before we even got to doing the simulation, we already made some regular effective source. And then the code itself is just sort of computing that effective source at each time step. And so for some of the other simulations, the effective source approach isn't necessarily necessary for their simulations, but for ours, because we need the full self force at every single time step, the effective source approach is extremely necessary to do what we're doing. Now, next I'm going to talk about the coordinates. I'll describe them first and then explain why we're using these. So we're using these sort of coordinates that are like this. These are our spatial slices. So this hyperboloidal foliation we're using has several steps. First, we use tortoise coordinates, which all tortoise coordinate does is, instead of having the short shield r, which is from 2m, which let's consider just from 2m to infinity, right? R star pushes 2m all the way out to negative infinity. So anything inside the event horizon is not even in the r star coordinate. Next, we compactify the radial coordinate. So spatial infinity is at some finite coordinate radius in rho here. So if omega for some finite rho goes to 0 in a limit, then of course r star is infinite. Now this has to be done very carefully to make sure that it is fine in the numerical scheme, but that has been done. And so then define these coordinates tau rho such that the radial coordinate asymptotes to null infinity. So this if we just did this step, all we'd get is spatial slices going along here, and we'd have put spatial infinity in the grid. But this part here is what instead makes it asymptote to null infinity, which we usually refer to as scribe plus. And so in the code, there's the sort of region that is using the tortoise coordinate, and then there's some layer where we transition into these hyperboloidal coordinates. Now, why do this? So there's several issues with evolving the system. So one, extracting numerical waveform requires extracting sufficiently far away from the system or extrapolating, right? So extending the numerical grid far enough is infeasible, of course. Now, extrapolating the waveform is difficult and not currently really viable. So people can extrapolate the waveform and extract it that way until a certain point, because the boundary conditions for the Emory system are not really clear. One could, in theory, derive them and implement them perhaps, but I'm not aware of anyone who does so. And so the only times I've seen an extrapolation of the waveform to get the extraction at infinity is, or at scribe plus, is if they simply, well, they don't talk about boundary conditions. So presumably they are simply simulating it until the boundary conditions reach the particle again, and then, well, you can't say that what you're doing is right anymore if you don't have boundary conditions at a finite radius. So most people are generally taking all of the spatial domain into their numerical grid. And then spatial compactification by itself significantly reduces the numerical resolution in the outer grid points, right? We've sort of compressed all space out there to be on our grid, and if we don't do something clever, we're going to lose resolution, generally speaking. So hyperbolidal coordinates resolve these by extending the numerical grid to null infinity for accurate waveform extraction. Of course, we don't have to extrapolate if infinity is just on our grid. And then we remove the need for boundary conditions because they're automatically satisfied with hyperbolidal coordinates. So the reason that happens is when we're doing this, the characteristic speeds for the ingoing and outgoing waves are either -1 or 1 in the sort of tortoise region. And then as we go out, the way we do this, set up this coordinate transformation to hyperbolidal foliation preserves the outgoing waves. So the characteristic speed is always 1, but the ingoing characteristic speed decreases, and at Scri plus is 0. So nothing can come into the domain, and the boundary conditions are simply to do nothing. And so we don't have to think about it any further or implement any actual boundary conditions, which is great. And then also the hyperbolidal foliation is constructed to preserve the numerical resolution out to Scri plus. And so sort of, if one wants to sort of think about, these are sort of, right, these are asymptoting to being null, right? So they're sort of, in some conceptual way, sort of following the waves out and to some degree preserving the resolution. There's, of course, much more technical proofs that it's fine and that it does in fact preserve numerical resolution. And that's all in, I can't remember whose paper it is, but there's a paper that talks about all of this for the hyperbolidal foliation and shows that it's all fine. We actually do 2 hyperbolidal foliations. We do one out here, right? But then we also do one on the inside because we've pushed the horizon to -infinity. So we can do the same thing on the other side. And in that case, of course, these are pluses instead of minuses. We're preserving the ingoing to always have a characteristic speed of -1. The outgoing speed starts at 1 and is 0 at the horizon. And it's more or less the same conditions, right? So that's sort of why we use hyperbolidal foliation and what it gives us. And then this discontinuous Galerkin method has been mentioned before today, I believe, but we also use the GG method, and sort of combines features of sort of finite volume and finite element. It's a finite element approach that sort of takes some hints from finite volume to do some clever things, basically. So the radial domain is divided into n elements, and then the solution within each element is interpolated with some nth order Lagrange polynomials within each element, and then fluxes communicate the physics between elements. This method has many beneficial features. There's 2 ways of increasing resolution. This is so-called HP adaptivity. There's no restrictions on the global grid structure. So one of the things about, say, finite difference is you have to have sort of the same grid spacing everywhere, and then you can introduce new meshes if you want a finer one. But this doesn't require that. So you can have your grid sort of be locally more refined without needing to do like meshes or anything like that. Like that's Carpet's solution to this sort of problem, right? Fluxes only depend on adjacent elements regardless of the order of the method. This is great for parallelism, and it also has benefits in that this is sort of what gives you what makes it not have restriction on the global structure, is that your stencil doesn't increase how many of the elements you're depending on. And then finally, the particles effects can be naturally included in these flux calculations. So since it's, as it's sort of the name suggests, discontinuous Galerkin method, so long as we keep the particle on some element boundary, we can just include the discontinuity of going across this point mass as part of the flux calculations. And so, of course, if one isn't on a circular orbit, that requires having these time-dependent coordinates that sort of follow the particle around. But still, it can be done. We have the time-dependent coordinates in our code. I'll sort of discuss that a little bit later. So Self-Force 1D is the name of the code here. It's the open source code for performing time-domain self-force computations. It uses the self-consistent approach to evolve Emory's using the full self-force calculated at each time step to drive the evolution. And it evolves the scalar wave equation in short-shelled spacetime, occurs in development as well. There's evolution equations for the metric perturbation in the irregular early gauge. These are in review for inclusion to the code, and then work for the Lorentz gauge is ongoing. So both of those are for the full gravitational case. Now in this code, the fields are decomposed into spherical harmonics, resulting in 1 + 1 dimensional PDEs to be solved using the method of lines. Or in the case of the gravitational, the metric perturbation decomposed into tensor spherical harmonics. Right? Now, this, while it is in the toolkit, this is now the first thing that does not actually use cactus or carpet, which I guess, thankfully they use thorn instead of spine, as we are thornless, but not spineless. It's fine. Yeah, so this section here, I'm partially including a lot of these bullet points, so they're all in one place. So if anyone wants to sort of see these again, there's this sort of 3 slides here that have a lot of details about the code, just sort of summarizing what techniques we're using and things like that. So we're using nodal discontinuous Galerkin method, as I said, to discretize the PDEs in the radial direction, and it can handle non-smooth features easily thanks to this, the nature of how the element boundaries have these fluxes, and that there's sort of a doubling of the grid points at the element boundaries. The point particles effects are incorporated through the effective source for generic orbits in a world tube approach. So this, I'm going to talk a little bit more about where the retarded field versus regular field is used and show the coordinates in a few slides. And then, of course, different coordinate systems are used for different parts of the domain. We have the hyperboloidal, near horizon, and scribe plus, and then the either time-dependent or tortoise coordinates in the middle around the particle. These generic orbits are evolved using direct geodesic integration with forces or oscillating orbits framework. So we have 2 time integration methods that are implemented, Runge-Kutta and Adams-Bashforth-Moulton. And so the way the code is set up also is the time integrators are completely agnostic as it regards to what sort of spatial integrator you're using or anything like that. All they know is there's some abstract class of equations that they're doing a time integration on, right? So if one wants to implement some new time integrator or spatial integration or new evolution equations, these are all somewhat decoupled in the code, right? It's very modular in that sense. And so the self-force, of course, can be extracted from the regular field at the particle location, and then we have observers to abstract the fields at horizon and scribe plus. We can also use initial data calculated in the frequency domain for eccentric geodesics for low L modes. So the reason for this, right, is we need some sort of initial data. But thankfully, if we start early enough in the inspiral, the initial data is effectively the same as the frequency domain codes, because the orbital parameters are changing slowly enough that it is effectively simply the solution to the frequency domain. So we can use frequency domain initial data to sort of prime the simulation. And then what we do is we let it sort of force it to be on whatever orbit we want, whether it's circular, eccentric, whatever. We force it to go around for a while until the sort of initial sort of bad data that's initially there, those transits leave and we're at some steady state, and then we can let it go. That's sort of the idea. So the back reaction, which is to say the thing that actually is going to push it off of these orbits, it can be turned on. There's still some issues with instabilities at late time, but that's still being investigated. But it can be turned on, and you can see the plunge. It's just in some cases it's still unstable. So the code requirements. So it's written mostly in object-oriented Fortran. The effective source code, which is provided by Barry Wardell, is in C++, and the initial data is in Python, and that's Niels Warburton. For the gravitational effective source, I believe Barry and Niels both work on that. Yeah, and the initial data that we've been using for the gravitational is from Seth Hopper, but none of that's in right now. So the only thing available right now is this effective source and initial data. So it does need a fairly modern Fortran compiler. Here's some examples of things it has been compiled with. Peter found that Ubuntu's G-Fortran fails with some internal compiler error. It's not a version thing, it's Ubuntu's internally, the one it gives you. I don't really know. That's just, Peter found that to happen, and who knows why exactly. It does need a C++ compiler, of course. It needs Python because it uses scons to build, and there's some initial data files produced with Python code. We do need BLAS/PAC, we need GSL, and then there's this documentation. And this documentation is produced by Ford, which is this Fortran documentation auto-generating thing, that as long as you write your code in the right way, it will take all of that and build this documentation of how everything links together, what parameters you have, et cetera, et cetera. So here's the computational setup, just sort of summarize again. We have the horizon at some row min, and then we have Scry plus at some row max, and in the middle, of course, is our particle. So in this first section, we're using the retarded field with tau row coordinates, and then at some transition layer, we change to using the either time-dependent or tortoise coordinates. And then once we hit here, we switch from using the retarded field to the regular field. And we're now in the region that has the effective source. And then we leave that and go back out to using the retarded field. And then we go through a second transition layer. We're in the outer tau row coordinates out to Scry plus. So that's just sort of the 1D setup for the numerical domain. So there are some future improvements and developments that are in progress. As I said, evolution equations for Reggie-Wheeler's metric perturbations are in review for inclusion. They've been tested for circular orbits and match the frequency domain results for those. As soon as we get an effective source for the eccentric orbits, we can compare and see how it does with that. But that is up for review for inclusion into the Einstein Toolkit and the code base that's available. There's other systems of equations in the pipeline. Tucholsky and Schwarzschild and Kerr are being worked on by various RU students over the years. And then also the Lorentz gauge metric perturbations have been worked on by me, but they're much worse than Reggie-Wheeler's are really, since Reggie-Wheeler's really is explicitly designed to make it as simple as possible, and it is basically just a different potential on the scalar wave. While the Lorentz gauge, you actually have to do the 10 coupled equations and evolve them together. And it tends to be very numerically unstable thus far. And though I've been working on that, but we don't have anything that is quite ready for inclusion. There's also checkpointing and restart that's been worked on by an RU student. As I said, the high-level code documentation explaining how the classes fit together from the Ford. And then this is, in addition to being in the toolkit, the Einstein toolkit, it's also in the black hole perturbation toolkit, which you will hear from Barry and Niels on Thursday about that toolkit. So hopefully the code will be a useful community resource and also inspire new developments for contributing back to the toolkit. And this is the bit bucket that it's at. And then this, I'm not going to really necessarily go over, but this is just sort of a slide Peter has that's just sort of talking about a lot of the features that are being used and such. So it's here in case people want to see it at some point. And now I'm going to stop here and see if there's any questions before I go on to the actual tutorial notebook. So does anyone have any questions about the self-force or about anything I've described and how we're sort of doing our numerical code? Yeah.
Just a clarification. Is it like you're just doing this in sort of the bring down area, or like all?
It's the whole thing. It starts far enough out that it the inspiral is that basically the orbital parameters are slowly changing, and then it's slowly after a while will go into a plunge. And then at the end of it simulates the Q and M ring down and everything. Yeah. Anyone else? Roland?
So correct me if I'm wrong. So you have some sort of gravitational self-force that works. What's kind of the largest secondary that you can simulate? What's the smallest part of the largest mass spectrum? That's closest one to one that you can get away with?
So it's kind of hard to say. So the way that these are that
It always works, but which one?
it always works, right? Well, that's sort of hard to say without having experimental data, right? I mean, I can always run it with anything, and because it's sort of perturbative, it's just you've already assumed that it's within the perturbative regime, right? So I don't have a good answer for that. I don't know if there will be a good answer until we have experimental data to see, how well we capture things. Yeah, and I mean, part of the reason that we want this code, of course, is also that this is much more accurate than all of the other methods. And so the hope is that people will be able to see what the difference is between this code and other codes, and I mean, obviously they can tell if, their code helps us see if we're doing something wrong. But on the other hand, right, we can see if there's any features that are potentially missing from those codes. And, it's a helpful feedback to have this sort of method. Did you have another question? Okay. Well,
So in principle, this is all still first order self-force, right?
yes, this is all first order. The second order self-force. So that's a Barry and Neil's question, to be honest. I only work the first order, but I mean, to some degree, it's more of the same in terms of framework. I mean, how stable it is. I mean, it's a lot of those just go into the source terms for the second order, if I remember right, if I remember those equations. Now, I mean, one can always just put that in and see if it works, but obviously I imagine that it's not going to be that nice. It's not going to happily go, oh yeah, cool, this just works. Wow, that's great. But I mean, I think if we can get the first order working on the self-consistent, at least that would be we would have a strong framework for extending the second order. Not to say second order won't also be a bit of an uphill battle, but yeah. But yeah, all this is first order for sure. Anyone else? Yeah.
So you said that it's part of two different toolkits.
Yes.
How do you do versioning when there are two toolkits?
So the black hole perturbation toolkit, as best I understand, is a much less sort of, it doesn't have static releases. It's much more of a collection of tools than most of them are like, there's independent Mathematica notebooks that can generate, so for the quasi-normal mode ring down, there's very specific frequencies that can be calculated at very high accuracy using frequency domain codes. And if we want those, there are Mathematica notebooks that will just give you either give you pre-computed ones for some of the lower L's or calculate them for you. There's just Mathematica notebooks to give those to you. There's lots of pieces of things in there. It's not quite the same as the Einstein Toolkit where it all needs to compile together and be happy, right? They're much more independent in that regard. So there's not as much versioning per se on the black hole perturbation toolkit side. Unless they've changed something that I'm not aware of.
So when you download the black hole
Yeah.
perturbation toolkit, I mean, what does that involve? Or is it just a list? Here are a bunch of GitHub repos.
I mean, yeah, I mean, there's a bit of sort of what do we include and what do we not, and there are, generally the ones I think that are included have a bit more sort of description to them. It's not like anyone could just come in and be like, oh, hey, I made this Mathematica notebook. I thought you'd like it, and just sort of drop it on the table and walk out of the room, right? But there's some degree, but it's definitely not, at least thus far. It is a much newer sort of toolkit, right? It's much newer. It doesn't have quite as much of the sort of formal nature as this one does. But of course, most of those things don't have to compile together. or things like that. So there's to some degree slightly less things that can go wrong, right?
And the follow-up question, are there any unit tests for
Yeah, so the scalar cell force code has tests of some sort. I know I have never run them,
Okay.
and I'm not quite sure how one does them, but I know they exist because that was a discussion that took place.
release, right? Oh,
But they will be running in the continuous integration server hopefully by the end of the summer. So that's one of the things that that's working.
Yeah, I knew there had been discussions about it, but I wasn't quite sure how it was being done. But yes, there are definitely tests for that. My regular Zerili code does not have any sort of tests like that at the moment. That will of course need to be put in at some point probably, but yeah.
gotcha.
Anyone else? Okay, looking to see.
I just,
yeah.
You said at some point in the
Yeah.
beginning about not being able to follow the physics of the quantum.
Yes.
And then when you answered that question, you said you follow the physics of the
Oh no, that's for adiabatic or frequency domain.
Okay.
So the adiabatic approach effectively what they're doing is assuming that the geodesic orbit parameters are changing much slower than the orbit. But in the plunge, that's clearly not true.
Okay.
And the frequency domain code, of course, is explicitly doing orbits. So both of those don't really capture the plunge. So that's why we want to do this, is because it's considering the full self force of each time step and letting it directly force it onto some path. Yeah, so that's sort of the idea of this, is to be able to capture the plunge. Okay, so and there's none in the chat, right? Let's see. Yeah, okay. So then we can go to the oh boy, it's Edge. Everyone loves Edge. The Einstein, that's not nice. Kids.org. That sounds right. Oh, can't reach it.
and an Einstein.
Yeah, I see that now. Okay, so if you want, those of you who were here yesterday will know how to do this, maybe. But if you go to the Einstein Toolkit website and then click here to go to the one for the workshop, and go to the program and click. It's in mine as well, right? Okay, and click the link to my tutorial. There's instructions on how to get to the tutorial server. And if you haven't made an account, you'll need to make one. And for that, the super secret password is lowercase m, lowercase c 2. So yeah, MC squared. Yeah, so you'll need an account for that. I think that's the right password. Oh, it was. Please don't save that. Okay, and the one you'll want is the carpet and self force tutorial. It's not Monday, but that's fine. It's this one. Okay. Maybe. Okay, and the notebook you'll want is the cellforce1d.ipymb. And is anyone having trouble getting to the server or still making an account? Okay.
So they'll be there.
Yeah, I'm just I'll wait a few minutes maybe to make sure everyone's with me. And I did update this, but I don't know, it may not have made it to all of the servers, but the update mainly just changed some of the wording to be more correct.
I have a server options thing that says I can do Monday.
Monday, you want Monday? Yeah. Well,
No,
that's,
but it is self-force. You see it is, if you look at the whole name, it mentions self-force.
Yeah.
okay.
And it is closer to Monday than it is to Friday.
That's, yeah.
I think we need infinity by this move. It'll work. Just give it a minute or so.
Okay. So this is just going to sort of go through how one downloads and runs the Cellforce 1D code. There's two examples. The second one takes too long to run for this, but it's there so you can see it, and I've already run it so we can look at the results. It takes about 40 to 50 minutes to run, but if at some point you know, it's in here, so if you ever download it yourself, you can sort of play around with it more. So, you know, you can, and I'm not going to rerun all of this because this here is going to delete, which I don't want to do because I do not want to sit here for 50 minutes and wait for the other one to run. So yeah, but you can go ahead and run these first few cells here. And then, so this is just going to clone in the repo. Oh, yeah. Oh, yeah. I forgot. It already knows that it's there. And then you can see what you got, and no one's complained that they've not been able to get in, except for you. But nobody else has complained, I should say. So, oh, something in chat. Oh, yes, I can do that, I think. Where's the... Is that good? Hearing no complaints. Okay. So yeah, so if we go into the repo that we just downloaded, so this sconstruct file sort of tells scons how to build the code. Now there's several sconstruct files that are in there. Basically, it's some of the big things is like, where is GSL, where is BLAS, where's LAPACK. So this is probably the first place to go if you're on some system that has put those somewhere weird, or if say you're wanting to write code, some of that's going to be in the sconstruct is where you're going to have to need to change things. So yeah, so this just makes sure that we have the right sconstruct set up for the machine we're on. And then I already have this installed, but if one is on a machine that doesn't have scons, this will install it. And then this is just sort of scons formatting. It's not a big deal, but yeah. So as I mentioned before, Peter found on a previous tutorial server that Ubuntu G4tran installations encounter some internal compiler error. This tutorial server doesn't seem to have this problem, even though it says it's an Ubuntu G4tran, so who knows?
So the trick is,
yeah,
Ubuntu has an optional GCC 10 and G4tran 10 that you can install.
Okay.
And those work.
Okay. So as long as you're using the Ubuntu G4tran 10, apparently it's fine. But if you're using the G4tran, was it 8, 9, whatever its default was, then you're gonna have issues apparently on Ubuntu. Who knows? Yeah. So if you do run this on another machine, this just sort of tells you what you're using, so you can sort of make sure that you're using something fine. And if you run into trouble, this would be a good thing to check, right? So then again, we're gonna go back to this directory, and then we can just build with scons. Now, the first time you build, you're gonna get all these warnings about non-existent include directories. As for, and this only happens the first time because it's not made a build directory yet. As for why it has these warnings, that is a Steve question, or that's a Peter question. Yeah, that's a Peter question, not a me question. So I'm afraid that I can't answer even if you ask. Did you have a question? Okay. So yeah, so go ahead. You can go ahead and run this. Mine's already built, of course, so it's only going to recompile some of the C stuff together. Yeah, so yours will take a little bit longer than mine. Yeah, go ahead.
What exactly is that?
So SCONS is just another compiling thing, like how make files, right? You can use make to build things, right? SCONS is yet another of those sorts of building things that puts together all of your different code pieces into one coherent whole. Hopefully, you know, it in theory will do that. But as make or CMake or SCONS, whether it does it or not, you know, but as long as it's all set up right, it will, you know, put all the pieces together correctly. I know at some point there was there was a bug with SCONS where it just couldn't handle the various modules and submodules in this, but Peter fixed it, and then I think they just accepted it as a fix. But yeah, so is it done building for you guys, by the way?
I made it finally.
You made it in, or you?
Oh, I mean, yeah, I'm in.
You finished building.
I'm on that.
Okay.
Well, yeah, I'm on this one too.
Okay, that's yeah.
Oh, the S-cons give me one.
Yeah.
Yeah.
That's
Oh, my.
expected. Yeah, that just happens the first time. That's fine. So I'll just go ahead and talk a little bit while that's building. So basically, when you're running the code, we're gonna make a place for it. So we're gonna make this examples directory, and then go into it and make this make a place for where we're gonna run the code and go into it. And I'm not running some of these because I already have these directories, so it's just going to complain if I try to run it. And then we're going to make this parameter file. And so while your SCONS is finishing up, we'll sort of talk about this parameter file. So the first thing here is, well, let me say first. So this params thing is one of the sort of newer, more modern Fortran features. So you can set up a way to read in a name list with a parameter file, and you have this ampersand params, and then the slash, those sort of tell Fortran where the list starts and stops. And you can have all of these different parameters that are read in by Fortran and set. And then, of course, in the actual code, you can set defaults and so on. So the equation name here is setting what evolution equations you want. So for example, if I was running the Reggie-Wheeler-Zerilli Schwarzschild evolution equation, right, then I named RWZ Schwarzschild, so I would just put that here instead of the scalar Schwarzschild, right? So this is just saying what exactly I'm trying to evolve. And then this next set here, these are setting up the GG method. So in elements is how many elements we want to discretize the spatial coordinate into, and then the order is what polynomial order we're using to interpolate within each element. This S minus is basically just where we're setting the horizon to be in hyperboreal coordinates, and then based on a lot of this stuff, it generates all of the other things, like where Scry plus will be and such. And then R center is the center of the Gaussian pulse, because this example doesn't have a particle in it. Right, so I should, yeah, let me go back. So what we're doing here, right, is we're gonna put initial data into the domain that's some scale, just some Gaussian in the scalar field, but we're not actually gonna activate a source. right? There's no particle. So what this is basically we should see is the same sort of behavior as quasi-normal mode ring down. If there's not a source, then we should see, if we look at a single radial location, we should see the same behavior as one we should see for the quasi-normal mode ring down, where it has this sort of damped sinusoid behavior. So that's the expectation when one just puts initial data with no actual source to drive it in this framework. The mass. So L min, L max is of course the L's that we're using for the modes. Because this is Schwarzschild, of course, all of the LM modes are evolved completely independently. There's no coupling between any angular stuff. But this just says how many we want to evolve, because of course, if we want to know the full waveform, we need to have a certain number of L modes to be able to, reconstruct the full thing. This is just saying how long we evolve it for. This is just setting up the Gaussian. What is our amplitude? What's our sigma? Use field observer true is tells it that we want to extract the field at scribe plus in the horizon. So we actually want to output that data. And then these numbers are saying how often we want to output 0D and 1D data. So has SCON finished now?
Sorry, can you repeat what is this use field?
This one, the use field observer true.
Yes.
Okay. Yeah. So basically, what this does is so the way that IO is implemented in this is that we have observers for things. So let's say I want to output the fields, right? It's set up to output the fields at scribe plus in the horizon. And if I want the field observer to be active, then I'd set this to true, and then it will, however often I have IO going, it will have the observer output the field. Now, of course, this also can be for things that are like reconstructed. Like, for example, in the Reggie-Wheeler-Zerilli case, one has to reconstruct what the actual metric perturbation is from the master functions. And so then you have some observer that calculates what it is and then outputs it whenever you request IO. That's sort of how it's set up. And so that's what this does. This is just saying we want to output the fields, basically. Does that make sense?
Yes, thank you.
Mm-hmm. Any other questions? Okay. Yeah, so you can go ahead and run everything up to here and run this, and then we can run the code. And of course, here it is OMP parallelized. We're just setting it to 1 because I'm pretty sure you're all only given one processor anyway, so I'm sure it would be be even slower if this wasn't true. So what we get here is basically output of a lot of the parameters we set up above in the par file, and some of the things that are calculated. So up above, we say our center, that's in Schwarzschild coordinates. So it then tells us what is an R star. It tells us the delta for R star between the things in the area around the particle, and just some other things like that. Yeah, and it tells us what the names of the evolution equations are, what output files it's opening, and here where it's extracting the fields, which of course we have it set to be the horizon, and scribe plus, which happens to be at this coordinate value. And then it tells us, so we don't set the delta t for these explicitly, right? It just automatically computes based on the spatial grid what the optimal time step should be based on the CFL condition. And then in this case, we're using Runge-Kutta 4, which is the one I've always used. I know the other one is in there. I'm Moulton's at the end. I forget what the name of it is, but the other method that's in there. I've never used it, but it exists. Yeah, so mine's finished. I'm guessing your guys' has as well. And nobody has screamed about problems, so I'm just assuming it's fine. So we can see here that we have a bunch of files produced by the code. So psi is the scalar field itself, and then we have rho and pi, which are the space and time derivatives. So the rest of these next few are basically just sort of importing NumPy and then importing the data. And yeah, so if we just look at the L0, M0, we have a bunch of columns here. So there's 5 of them. The first is time, unsurprisingly. The second and third are going to be the real and imaginary at the horizon. And then the next 2 are the real imaginary at null infinity. Now, of course, since all of the initial data was real, the imaginary components are 0, which is nice. Yeah, and so in the case of some things like the regulars are really, you're going to have things that will be complex, but then they reconstruct into the actual physical quantities. They're all real, right? So some files, depending on what you're looking at, might have imaginary components, but for anything like that's actually physical, of course, you should see that these are all 0. So we can then extract these into sort of other names, and this is just going to be like, hello, you already have all these, but so basically these are just saying what L that is and where we're extracting it at. So that's, instead of having this sort of just where it is in the file, these are sort of more intelligible names. And then we're gonna pull in the matplotlib and some other stuff, set some parameters just so the plots look like we want them to. So this is L0, M0 in a log-log plot. We're plotting both the horizon data and the future null infinity data. So the way that, since this is a QNM ring down, at the late time, it goes into just being this sort of power law decay on the tail end, and they have very well-defined ways they go based on L, and we see that as they decay away, they approach the expected decay rates. And so these talked about here about how what the formula is, but yeah, it's just based on L. And so we're going to see that again for the other ones. But first we have this is L1, M1, but it's just a log plot and it focuses on the actual ring down section of the data. And so both horizon and null infinity are going to have the same frequencies, assuming it's right, and they do. And so here we see that the black line is the exact damped sinusoid, and then it's just right on top of the data the whole way down. And that's what one would hope for in a accurate calculation. And so that's just sort of, and these QNM frequencies are from, the expected frequencies are taken from Emanuela Berti, and here it's in the page if you want to see where it's from. And so these other plots are basically the same thing, but for the other L's. And so we see again that we match the tail on the power law decay, and we have the right QNM. Now, one thing you might notice is that in this case, we only have the L0, M0, L1, M1, and L2, M2. So the I think there might be an L2, M0 somewhere. But the thing about the scalar case is that you actually only end up with modes where L plus M is even. So you don't have like L1, M0 or L2, M1. None of those are present. They're present in the gravitational case, but for the scalar case, they're not there. So that's why those simply are not present in this data. Yeah. So let me go ahead and. So yeah. So again, now on this one, this is the L2 M2 mode for the log plot. So at Scri Plus, we've got a pretty nice sort of power law in the end, but for the horizon, it's already decayed so much by the end of the Q&M frequency mode that we've just hit round off error. So we don't get that power law because it's already so small that we can't see it. So that's sort of why we don't see it on this one. It's just too small already. Yeah, I mean hypothetically, so the way this code is set up, you can change. It has everything set up to use this working precision. So if one were to change the working precision from double to quad, maybe it would resolve. You can see that. I don't know. It depends on what exactly the source of I'm pretty sure that's just pure round off. So so if you changed it to quad precision, maybe you would be able to resolve it. But
Have you ever tried that?
I've not.
It's rare that.
I mean, I don't think it's likely. I just said it's possible.
Like 10 minus 17.
Yeah. So I mean, yeah. I mean, at that point, it's basically zero anyways. So it's fine. Yeah. So the next example, I mean, if you try to run it, it's not going to finish. So I guess I can't stop you from running it, but you're just going to watch it and sit there. So what we do though is that we're going to look at a scalar particle moving along an eccentric orbit around a short-shelled black hole. For the parameter file, we're first of all going to use initial data in this case, which is, like I said, from the frequency domain code. And so we've also increased our resolution in the number of elements quite a bit, but we've actually reduced the order. Simply, we don't really need as much order, but we do need way more elements for this. We've moved around some of the S- and stuff. P orb is the semilattice rectum because this is an eccentric orbit that we're on. And then of course the eccentricity. Now T size, what this does is this tells it how much of the DG elements you want in the tortoise region, right? So you have, or in this case, time-dependent coordinate region. So you have that middle section that's time-dependent coordinates, and we're saying we want 25 of the elements to be in there, and the rest of the elements would be symmetrically on either side. And then we're going up to L max of 5. And since we do want a particle this time, we're setting use particle to be true. And then, yeah, and we're running it for a little less time, but it takes way longer, of course. So that's, all of this is just sort of setting up the things that are going to handle the world tube and making sure that the orbit's using the right forces and stuff. And this is setting how big we want the world tube to be around the particle, right? Because that decides how sort of smeared out the effective source is. And again, the use exact initial data is what's going to access this initial data up here, right? And so, and we only have initial data up to L max of 2, and then we tell it where it is. Now, the reason that we're only using initial data for some of the L nodes is because if one were to do a one with the back reaction on and do the full inspiral, We have to wait for the transients to decay away and reach the steady state solution for whatever orbit we're on, right? And the initial data helps us get there faster. But the thing is that the transients decay rate is, if I remember, exponential with L. So sure, you could include initial data for all the higher L's, but it doesn't gain you anything. As long as the first few L's have initial data, all the other L's will have already converged to whatever they're going to converge to by the time those lower L modes have converged to the right solution. And then in the case of doing a simulation, you would then, let the particle go. In this case, we have, I believe we have. Oh yeah. So the turn on source smoothly is another thing that isn't immediately obvious what it does. So the source is always turned on smoothly in the case of not using initial data. And what that is if we were to have zero initial data and just let it go, then we've effectively have this sudden discontinuity in what's going on, because suddenly we've said, oh, there's a source now. So what this turning on smoothly does is trying to make it sort of smoothly transition into having the source be fully active. And in the case of initial data, you need the source to be on as soon as you start for those L modes, because otherwise the initial data is going to be for the case that the source is fully active, but then you don't have the source fully active. So it's going to do something weird. And then you turn the source back on, and then it's going to do something else. Eventually it'll converge back to the right answer, but you're basically defeating the point of having good initial data if you turn it on smoothly for the L modes that you're actually including initial data for. Yes.
Sorry, you may have said them, I just missed it, but how are you modeling the?
So it's the effective source approach, which is in terms of how it's a really big code that just sort of, to be honest, that's a Barry and Neil's question. They're the ones that sort of provide that, but like the way it works is they define some effective source and then have some effective field that comes from it, and say that it needs to match the regular field up to some order, and that it's approximately correct to some degree. And no, it's something. It's fine. Go ahead, Roland.
So I can't give you the details how to do this, but it's fairly complicated. The point is essentially these things are like point charges initially. We will the Coulomb field, but you say they're inspiral, and the Coulomb field doesn't exert a force on the central charge. So why do this now? Force to this value because it's Coulomb field isn't come by. There is a kind of a field that scatters back to it, follows the light waves, and you can extract a bit of the field that is into it, but this extraction that does not exert force from the part of the field that does exert the force that is finite. That finite piece that does actually exert the force is that effective field force that's being computed here, more or less.
Basically, yeah. It's basically you're looking at what part of the actual sort of how do you say what is causing the force based on some effective thing that approximately is the same, generates the same regular field as if you explicitly subtracted off the singular field from the retarded field and got the regular field? Like how do you get some effective source that gives you the same answer within some region, right? And then the window function just makes sure that outside of the window function, the regular field and the retarded field are the same, so that you can just use the same field everywhere. That's basically the idea of the window function for the most, like another reason to use the window function. But yeah, there's not a nice clean way to describe really what the effective source looks like or anything. It's a very complicated expression, and it'll be even worse for the gravitational case. They have it for for first order.
How much of your time do you now spend computing the vector self force compared to actually solving the remainder of the equation? Remember, for the 3D code, you had to parallelize that out and farm it out from the node to help the self force position.
Sorry, can you ask again?
I think for the 3D code that Peter had at one point, he had to actually farm out the computation of the regularized source to nodes other than the node it happened to hold the physical location of the particle. This was so complicated that he had to regularize that.
So I personally prefer to treat the effective source as a black box as much as humanly possible. So I'm not entirely sure how all it's parallelized on that end, right, in terms of the effective source itself. But I mean, it's more or less just called by at some point in the evolution, it gets called and says, hey, I need the effective source now, right? And then it computes it. It's not, it could be hidden somewhere, and I'm sure something is, hidden in there but it's not like doing anything too crazy that I'm aware of. But yeah, I mean, also the full 3D was a lot more expensive, I'd imagine, for the effective source, especially, right? Yeah, I mean, I don't know either. I only ever worked on the 1D code, so I can't really speak too much for the 3D code. Yeah. And then the T sigma and T order are just saying basically how exactly we turn on the source for the ones that are being turned on smoothly. I found for the Regular Zerilli that it was important to have this T sigma be somewhat small, because if you have it too large, then you actually end up accumulating error in the psi function, because the d psi dt is wrong for a little while, right? But it eventually converges to the right answer. But psi, of course, accumulates all those errors. So if you don't turn it on fast enough and get it to sort of converge to the right answer, then you're sort of accumulating all those errors. So you want to make sure T sigmas are small enough to cut down on the errors that can come from that. Yeah, and then this is just saying like what the charge of the scalar charge of the particle is. And we're not evolving it, we're just sort of forcing it to stay on the orbit. And then one can also use the last few L's to fit to get higher sort of effective stuff from the higher L's. I don't know exactly how that works, but we're not using that. And then output coords for exact. The reason you would use this is, let's say you wanted initial data, right? This will output coordinates that are in the format for the frequency domain codes that we use. So we can then give it the exact coordinate setup we're using, so that it will tell us exactly at the coordinates we have what the initial data is. So this last thing is for the actually getting the initial data. So you would just like put it at like, basically don't actually run the code, right? Just have it set up, the coordinates, have this set to true, it prints out the coordinates, you go over to the frequency domain code, tell it these are the coordinates I want initial data for, and it gives you the initial data, and then you can come back here and use the initial data. That's sort of at least the current system for how one would do that. Yeah, and as I said, this next block will take a long time to run, so we won't be, well, you won't be finishing it if you start it, at the very least. So again, oh yeah.
Can I increase the number to make it faster?
Probably not on the tutorial server, that's for sure. I mean, it'll run faster if you give it more threads in theory, but not on the server. Like, I mean, it's a parallelized code, but on the server, you don't have more threads to work with.
There are 2 threads actually.
Oh, there's 2 threads,
Very
maybe.
generous.
Wow.
Good. Let me just get it up. Yeah, maybe there's 2 courses.
I get it to run on your laptop. You can run the Docker image on your laptop.
Yeah.
Find out how to do that.
I'm currently running one.
I mean, you can tell it as many threads as you want, but that may make it slower.
If I said two, then
No, if you have four, it will pretend it has four.
Yeah, it'll put as many threads as you say, but if you have less cores than that, it'll put multiple threads on one core, so it'll get slower instead of faster.
Right, so it's gonna, even if you have one thread, it's gonna give you the illusion of multitasking threads doing these various things. And if you ask for four, it's just gonna try to do four and two.
four.
It's gonna use the same two, it's gonna keep swapping things in and out.
I did just write it down. I didn't-
Are there any other questions from anybody? Okay. Oh, yeah, go ahead.
There is also one thing in the maximum population.
Sorry, I couldn't catch everything. There was.
So there is also a set for one code in the maximum population.
Yeah.
So is it, I mean, how different is this from that one?
They're the same. They're the same code. I mean, obviously, if you check out one from, say, an Einstein Toolkit release, and you check out the one from the Black Hole Perturbation Toolkit that I assume probably checks out master. I mean, there may be slight differences because it's not the release like frozen version, right? But it's the same code. Yeah. So yeah. Regardless of which toolkit you go to, it'll be the same. Yeah, so this is the sort of the output for all this, and it's, more or less the same. And here we see it's sort of pulling in the effective source. Now, one thing we notice is right here, it says to turn on the source smoothly, we're using this. So this is because we changed how we want it to evolve while we're turning on the source. And so because we've, and in order to do it properly, it needs a slightly different time step. And so then as soon as it's done with that, the source is fully on and it goes back to normal time steps. So it just does it for the short little time it needs it, and then it goes back to normal. So that's just sort of another little thing that if you were really looking through all these lines, you might notice and wonder what it is. That's sort of what this is talking about.
So this is kind of a related problem. In Cupp, when you start a simulation, right, you have this option to enable all the time levels in a bad way. You just copy the data, copy all time. Right? There is a way of doing something similar to this where you start with a DT very, very tiny. You sort of ramp it up as you go, and ultimately achieving your desired DT a little bit later. And I don't know, is that something? Is it even useful given the existence of carpet X? Because carpet X is understanding.
But it would still be useful, right? I mean, that's what you had this in the paper.
Yes.
To get rid of the junk more quickly.
Exactly.
Yeah, but that's independent of the driver. That's just in some sense it's what Baikal or Lean or Black. I mean, it's
It could,
essentially where you can.
it could be done with drivers.
Yeah, it would never be actually in fact with the driver because the time step is actually controlled by the time point. But yes, the driver is just told. Carpet basically has to query the time point once iteration. What's the current time step I'm supposed to use?
Yeah,
the time point. Yeah, the time step. You will have to be careful though if you do that. At least by changing extra time step, then Carpet will say this is now adaptive time stepping, and it will probably yell at you for various reasons. I think you just modified the last.
the last condition will do.
That might be,
All this is equivalent to just the gauge.
that might be the easiest way to do it in the grand framework, because then everything still has the same time step. It's just that now the coordinate time means something different.
Okay.
And it's just
It's fine.
reminded me of something very
Yeah.
familiar.
So this is all just going to again sort of grab data and plot it. So here we're going to plot the radial component of the self force as a function of time. And so because we're forcing on an orbit, once again, we're sort of expecting these to converge to nice values, and that sort of change as it goes through the orbit because it's eccentric, right? And we see that sort of over time will sort of go through this sort of pattern. Yeah.
So this is just a fraction of the orbit that you're showing us.
A fraction of the what? Yeah, so this is the actual XY. Yeah, so this is the XY that we have. I don't know which way it was going, but one of these ways. Yeah, and so yeah, so that's what the orbit looks like. And then this is the R coordinate of the self-force over time. Yeah, go ahead. What? M, big M. It's the mass of the central black hole. That is the usual unit that we tend to use for the self-force things. Is everything's an M, big M. That's it. Yeah, so let's see, this is the radial components, of course. Yeah, so the I think that's just it converging to sort of what the long-term solution is, right? And I think it might just take longer to converge in this case because it's an eccentric orbit, right? This is this is the radial component of the self-force, right? Because the self-force has multiple components, so that's why it's not like some single value, right? It's changing over time because it's the radial component, but there's a little bit more noise in the beginning just because it's still got sort of stuff propagating out, right? And then but you can already sort of see that it's following the curve. There's just some noise to it, right? But yeah, and the idea is that once you had it sort of on a clean orbit, then you can let it go and it can evolve by turning on the back reaction and everything. But yeah, so that's just sort of that's all I have in this notebook in terms of how to run it, how to download it. I will go ahead and show you. So if you followed the link in the PowerPoint, this is what it takes you to for the documentation. And so these are just some of the things, but let's say I wanted to look at all the modules, right? I can then search for, say, I know one of them is called parameter because the parameters are in this module called parameters.f90. And then if I click on it, it tells me everything that uses it, which of course for parameters is a bit useless. It's everything, right? But then it also pulls out from the code all these details about all of the names of the parameters, what they're initialized to if you don't set them, a description of them, what type of variable they are, whether they're public or private variables. Not that we are really using that, but they're all. But yeah, and let me go into source. So this is getting generated from this file, and so the formatting here, right, is that we have this module, and it's the definition of all parameters, which is what gets converted into this description on the previous page, where it's here, right? So that comment comes here, and then the comments for all those.
Sorry, which page is that again? I think that I lost here the link.
Sorry, let me I can copy it into the chat, maybe. Will this let me? Oh, I bet if I go out, can I select text? One of these lets me select text, surely.
It's the cursor one?
This one? Yeah, okay. Let me find. Yeah, okay, I can post, please don't click it, just let me have it, just. Okay, I will post that in the chat. I mean, it's also in it's also in the slides. So if the slides, I assume, well, if they aren't now, will probably be in the program at some point. Yeah, so that's the link to this documentation stuff. And then if you wanted to get to the actual code piece I'm looking at, you would go back into your hub, click Cellforce 1D, source, parameters, and then there's the file. But yeah, so in here we see there's all these comments for what are these variables, what do they do, and all of that gets pulled into here, right? So as long as somebody follows this formatting properly, if somebody wanted to add to this code, right, as long as they follow this sort of formatting for the module, then it will get, and they run forward on it, it generates all of this documentation about variables and how all the different pieces are connected automatically. So yeah, it's a very nice sort of feature that Ford has for Fortran. But yeah, so are there any questions for me? No? Okay.
So I'm just like clicking around.
Yeah.
In the documentation.
Yes.
And occasionally I'll find like bits and pieces of source code.
Interesting. Where are you at?
I'm in module RK5.890.
RK5.
RK5. Yeah. So I'm trying to find like the meaty part of this. So I click up at the top, there's source file, and then it shows me something that's not very meaty. Some very generic stuff.
Oh, so you're wanting to see, so
see what's going on.
So the way the modules define everything inside. The submodule is what implements things. So if you look at the files dependent on this one at the top of that page,
Submodule.
So files dependent on this one, you have the submodule for RK5, and then you have all integrators, right? And then you have these different implementations that link into this, right? So the idea is that you define these abstract classes, and then you get more specific as you want things. So as another example, oh, sorry, do you need me to go back?
No,
Okay.
I got it.
Where is it? Trying to think of the right name. Just equations, right? So if I look at equations, right, this splits into PDE equations and ODE equations. And then for the PDE, right, we have the scalar Schwarzschild. And then I would have another one that would split off now that would say RWZ Schwarzschild, right? So you can see sort of how things are inherited, right, as well.
This gets more abstract as you go to the left.
Yes, the left is the most abstract. There are equations. And then the right is much more specific, yes. And the way it's set up is the modules are where it says these are the variables, these are the functions that are being inherited or whatever. And then the submodules are where the actual real sort of implementation code is. So it sort of divides the implementation from saying what's there. And yeah, so that's the sort of methodology for the code.
Gotcha.
Yeah.
Cool, thanks.